Hello again, everyone. Let's go ahead and cover some ideas about the notion of limits, which are typically covered in section 2.2 of your notes. So in the past and last week, we talked about the ideas of having graphical connections to various functions, and then having that idea give rise to how it is we're going to examine the notion of limits. What I would like for us to do is examine a function such as x squared minus 4x minus 5. Notice that I just put that into a graphing utility. This could be GeoGebra, like I illustrated with you in class, or it could be your traditional graphing calculator. And very quickly, we can see that the y-intercept will be at 0, negative 5. You can just input 0 for the x's, and then get a y value of negative 5. That's right there on the graph. And then to get the x-intercepts, that implies that it's going to cross the x-axis. So if it's going to cross the x-axis here, the y values would have to be 0. And we would get 5 and negative 1. You can get that algebraically by factoring this expression to give you x minus 5 and x plus 1. That factor will give you 5, and x plus 1 will give you x equals negative 1. And then the vertex of this parabola will take place at 2, negative 9. Now, if this is the shape of the parabolic function that we have, then I want you to think of limits as the value that the function approaches as we get infinitely close to any one x value. So for instance, if you think about the x value of 5, what I want us to consider, as I've written out for you, is that as we get infinitely close to the x value of 5, imagine what happens right here. From the left and the right, so imagine as you get infinitely close along the curve, that's a very key point. It's always going to be along the curve. So as you approach the x value of 5 along the curve, the y values are getting closer and closer to 0. Similarly, take this x value of 5 and along the curve approach that x value, and notice that the y values, as we approach it from the right, we're also getting closer to 0. So what that means is that we would say that as we get infinitely close to the x value of 5 from the left and the right, the function value, or the y value, is approaching 0. Mathematically, instead of saying that long expression, we can just say the limit as x approaches 5. Notice that there's not a plus or minus here, so it's not strictly from the positive side or strictly from the negative side, meaning a one-sided limit. The two-sided limit, as we approach 5 from both sides of the function, will go towards 0. So that's one quick illustration of how it is that we could in fact evaluate this limit as x approaches 5 of the function f of x. And notice that as we approach it again from both sides, the function is going to approach the y value of 0. The next thing that I would like for us to do is go to the book and then go over some of the examples that they give you in section 2.2, which is titled Limits, a Numerical and Graphical Approach. So this is where we've paid it forward one more time by talking about the function, its graphs, and how it is that numerically, graphically, and functionally we can begin to make sense out of the mathematics. So your book goes through and they start with a rather complicated function, f of x being sine of x over x. I'd rather hold off on that and actually zoom forward just to show you the definition and then a couple of easier examples to think about. The first one is that the definition of a limit, that as we talked about in the previous example, the limit expression itself, once you understand the parts of this definition, is not a hard one. So it's the limit as x approaches c of the function. This will equal the limit L for limit. So notice that our function has to be defined for all of these x's in this interval containing this value c. And it's what we are approaching, not necessarily at the value c itself, but it's what we are approaching. Limits are all about tendencies and what you're approaching. So we would say that in that case, the function is approaching or converging to L as x gets infinitely close to c. We'll talk about this theoretical definition in the middle during class. So here are a couple of very quick limit expressions. The limit as x approaches 7 of 5 equals 5. Well, that ought to make sense because 5 as a function or as a graph, it's constantly equal to 5. So it doesn't matter if you're approaching as the x values get closer to 7 or not, a constant function is by definition constant, so that limit should always be 5. Now the second example, part B of example 1, limit as x approaches 4 of 3x plus 1 equals 13. There are two ways you can take a look at this. You can either go through and you can analyze what happens with this graph. You can visualize what 3x plus 1 would look like, and then try to approach 4 from both sides. What some other people do is they also evaluate this numerically. So they try to see what would happen if they take values very close to 4 and they were to input that in for x. In this case, if you were to take a look at 4 itself, 3 times 4 is 12, 12 plus 1 gives you the 13. We'll talk about both when you can and perhaps should examine it that way, but also some of the dangers in just looking at things numerically that way. What I was suggesting about a constant function is that notice that the limit as x approaches any value c of a constant will equal that constant. But to continue with the graphical and numerical investigation, let's take a look at another couple of examples. Now, example 2 looks kind of complicated. Limit as x approaches 9 of x minus 9 over the square root of x minus 3. Now that's not a graph that we would know what it looks like right off the top of our head. So if you look at the graph itself, as we get infinitely close from the left and from the right, so we're going to approach the x value 9, because that's what our limit is asking us. We're going to approach the x value 9 from the left and from the right. We see that the y values are getting closer and closer to 6. So we anticipate that the y value will be the limit. So the limit as x approaches 9 of this expression should equal 6. That's the graphical way of looking at it. I would suggest you actually take your two thumbs and then place your thumbs where the blue arrows are and get closer and closer to the x value 9 that way. And then see what y value you're approaching. That should serve as your limit. But this is where table 2 shows us graphically or shows us numerically what is happening. So as we approach 9 from the left, that's what this negative sign right next to the 9 actually is suggesting. So this is 9 from the positive side, this is 9 from the negative side. Notice that the values of x are getting closer and closer to 9, but it's 8.9, 8.99, 8.999, so forth and so on. Look at the function values. These values are also getting closer and closer and closer towards 6. So the limit as x approaches 9 from the left of this function seems to be going towards 6. Similarly, the limit as x approaches 9 from the right of this function, notice close doesn't mean 12, 11, 10, and then towards 9. You have to get pretty close numerically, such as 9.1, 9.01, 9.001, so forth and so on. And if you compare that as we get closer and closer to 9 from the right, we notice that the limit is again approaching the value of 6. So we would say that the two-sided limit would be, in fact, 6. What happens to the limit of a function, such as x squared? Well, that goes back to the very first example that I showed you. Limit as x approaches 4 of x squared. We anticipate if you were to take 4 and plug it in for x, you would get 16. But now look. In this case, that limit would be equal to the function value itself. This is true, in fact, when our function is continuous. This is why we spent so much time talking about the domain last class, because if you have a nice continuous function, then you can actually count on doing such things where the limit would equal the function value. Graphically here, we see that if we have 4 and we approach 4 from both sides, as we approach the x value 4 from both sides, the y value seems to be approaching 16. You can see that numerically here, approaching 4 from the left, we're getting closer and closer to 15.999, close to 16. As you approach 4 from the right, this way, then we're also getting closer and closer to 16. The last example in this section is again a pretty complicated one. This is not one where if you were to take 0 and try to input this in for h, you get 2 to the 0, which is 1. 1 minus 1 is 0, divided by, if you were to put in 0 for h, you would get division by 0. Well, that's not defined at 0. But if you were to look at it graphically, as the values of h are getting infinitely close from the right and from the left to 0, this seems to be approaching a value somewhat less than 1. We can analyze that numerically, and as we're getting closer and closer to 0, it seems to be approaching about 0.693. If we do that from the right, we also see that we are approaching about 0.693. So sometimes we have to at least rely on the graphical and numerical techniques that we have to help us out. And then there are other times when a limit that we have simply doesn't exist. So if you take a look at this almost accordion type function, where as you get closer and closer everything is jumbled up, but then you can stretch the function out to look at it, this is the function sine of pi over x. Now, as x's get closer and closer to 0 from the left, so our x values are getting very close to 0, but from the negative side, notice that there's not a clear trend. The function values go 0 to 0.86 to a negative, to another positive, to another negative, so we're not really converging towards a single value. The same thing for as x's approach 0 from the right. As we get infinitely close towards 0, the y values, the function values of sine of pi over x, then these go from 0 to a negative, to a positive, to a negative, to another positive. So again, that limit as x approaches 0 from the right is not really converging towards a single value. So we would say that this is a limit that does not exist. Similar to what we've talked about up until now, we can have two-sided limits where we are approaching the single x value from both sides, or specifically you can just think about a one-sided limit. So if we're going to consider a one-sided limit, then think about what happens with limits as we approach it from the left or strictly from the right-hand side. A good example of that would be the function f of x equaling x over the absolute value of x. Graphically, this is what that looks like, which curiously enough, if you look at the right-hand portion of this graph, it seems to be equal to 1, and the left-hand portion of the graph, it seems to be equaling to negative 1. Algebraically, that ought to make sense because the absolute value of x for values that are positive then would take on certain values, and the absolute value of x when x is negative would actually equal negative x. So for x's that are less than 0, like you see it here, for x's that are less than 0, the absolute value of x becomes negative x. So this ratio equals negative 1. That's why you have that part of the graph. Now, for the x values where we have positive x values, absolute value of x would equal x, so x over the absolute value of x would equal positive 1. That's this half of the graph. Notice that in either case, x equals 0 is not in our domain, because that would make our denominator equal to 0. So if we were to take a look at one-sided limits, limit as x approaches 0 from the right would equal 1. Here's 0. Approach it along the curve from the right, we're approaching the y value 1. And the limit as x approaches 0 from the left, along the curve, as you approach 0 from the left, that would be going towards negative 1. That's where you see this one-sided limit. This would be a good example, though, that the two one-sided limits exist from the left and from the right, but the two-sided limit, if you were to simultaneously think of what's happening as I approach 0, well, from the right you're going towards 1, from the left you're going towards negative 1, so the two-sided limit here would not exist. However, the one-sided limits, as we illustrated, do exist. Lastly, if you have a funky function like you see in figure number 7, you could ask about, or you could be asked about different limits as you get very close to x values from the right, from the left, or from the two sides. So notice that in this case we're going to take a look at specific values 0, 2, and 4 along the x-axis. Let's actually start with 2. As you approach x equaling 2, from the right-hand side along the curve, the y values seem to be approaching 1. So the limit as x approaches 2 from the right would equal 1. That's what you see here. And, well, what would the limit as x approaches 2 from the left be? Here's 2. Remember, we're going to always approach it along the curve. So as we approach it from the left, that would be along this portion of the graph, the y values seem to be trending towards 3. So the limit as x approaches 2 from the left of this function would equal 3. Lastly, take a look at x equaling 4. So if you approach the value 4 from the left, it seems to be going towards 2. And if you approach the value 4 from the right, it's also going towards 2. A common misconception is students see that that point is not there. But remember, limits are about what you approach. So from the left and from the right, we are approaching the y value 2, so that will in fact end up being our limit. It's with two-sided limits, it's about what you're approaching, not necessarily whether that point itself exists or not. Later on, when we get to the topic of continuity, that point will be made very clear. So in this case, the two-sided limit as x approaches 4 of the function will in fact equal 2. The last type of limits that are discussed in section 2.2 having to do with limits are called infinite limits. As the term suggests, I'll go over the infinite limits have to do with infinities. I'll go over some of this terminology with you through the example. So in example 8, notice that they've said it's a GU, meaning you can use a graphing utility to see what happens. We're going to take a look at the one-sided limits graphically. Now, this is an example of a rational function where x equals 2 is not in our domain. So we anticipate that at x equals 2 we should have a vertical asymptote. So if we have 1 over x minus 2, its graph will look something like this. At x equals 2 we should have a vertical asymptote, and you have one part of the graph that goes down this way and another part that goes up pretty fast. So if you were to take a look at the limit as x approaches 2, from the one side, from the positive side, again along the curve, as x gets closer and closer to 2 from the right-hand side, the function values are going towards positive infinity. And similarly, the limit as x approaches 2 from the left, we're going towards negative infinity. So this is when you will see that the one-sided limits, the limit as x approaches 2 from the left of the function is equal to negative infinity, because we're going down like that. And then the limit as x approaches 2 from the right of this function, as we approach 2 from the right, we're going to approach positive infinity. So that's what we would get for the two one-sided limits. Now, the two-sided limit, if we were to examine what is the limit as x approaches 2 from both sides, one side goes towards positive infinity, the other side goes towards negative infinity, so we would say that the two-sided limit as x approaches 2 does not exist. So that's just another example that we can take a look at. Your book goes through and actually goes into more detail about that. But the summary of section 2.2 has to do with the language that we use for limits. We've covered that in this video. Also, what happens that as the function, if the function itself doesn't approach a limit as we get infinitely close towards a value c, we say that that limit does not exist. That's exactly what happened in the case of the limit as x approaches 2 of that rational function. That two-sided limit as x approaches 2 did not exist. We've also taken a look at one-sided limits from the left and from the right. And for the limit to exist, we need to have both one-sided limits to exist and to in fact be one and the same. So from the left and from the right, they have to be going towards the same value. And then if they agree, then we say that the limit exists.